Okay, we'll give it a minute for people to join. Right, okay, let's crack on then. Hello and welcome everybody to our third of 5 webinars series. I'll introduce the list of panelists today. So Dr. Wang, he's our presenter for today. Wei is the focal point at CSCP. And Yunan Gao, he's the current president of ICOR. And we've got Steve Tate, who was the previous president of ICOR. And we'll start with the brief introduction of ICOR, and it's going to be presented by Steve Tate today. Steve.
Good afternoon, everyone. Welcome to this very special joint event between CSCP and ICOR UK. I'm just going to briefly introduce the Institute and then hand over to my colleagues at CSCP. Next one, please. So we have been in discussions with CSCP for about 12 months now, and we have made 2 visits so far. My colleague, Dr. Yunan Gao, made a visit in the summer, and we both went in October. But as I say, we've had many meetings, and this culminated in the signing of a new MOU agreement in October 2024 at the International Corrosion Congress in Xi'an. Next one, please. As Mei-Ling mentioned, in the past few days, Dr. Gao has taken over from myself as the new ICOR president, but we should be working together very much for the next 2 years. I shall be supporting the new president in his role very much. Next one. We were founded some 65 years ago as the British Association of Corrosion Engineers, now known as the Institute of Corrosion. We are based in Northampton near London, and we have 8 regional branches around the UK, and now expanding overseas to provide a better service to our members. Our principal aim is to advance the understanding of corrosion and corrosion control education, and to facilitate the exchange of information and ideas for everyone's benefit. Thank you. These are our current branches around the UK. As you can see, they're fairly evenly distributed. UK has a population of about 70 million people, of which about 60 million are in England and about 5 million each in Scotland, Wales, and our colleagues in Northern Ireland. Next one, please. As I said, we are looking at some overseas branches. We currently have about 1,500 members, with about 400 of those based overseas, so hence the targeting of some overseas expansion. We do have quite a lot of company members, about 150 companies supporting us, as well as our individual members. Next one, please. We have a very good journal that we've recently expanded, so we aim for a minimum of 3 technical articles in the magazine, which is published 6 times a year. So everyone is invited to contribute articles for possible publication. So just send those to our editor at icor.org, please. Next one. We welcome any applications for membership for whichever grade, technician, member and fellow. You can apply directly for these if you have sufficient experience. And later on, you can also upgrade to chartered engineer status, if you seek to become work at that level, Thank you. We have two main divisions, our Corrosion Science division, which obviously works very closely with universities, and we present student awards and an annual award also to the most notable professor in recent years contributing to corrosion science. Thank you. Our corrosion engineering division has several technical working groups which work towards developing new technical standards and resolving issues in the industry from an industrial viewpoint, and to have a strong networking with fellow corrosion professionals. Thank you. We currently have our Young Engineer program, which is part of our Young I-Corps division, coming to a conclusion today with their 12-month program of training and case studies. So the winning group from that 24 intake of this year will be going to the AMPP conference with travel sponsored by BP, British Petroleum. So that is something we currently do every 2 years, but we're looking to try and do that annually if possible because of recent high demand. Thank you. And we also have our new scholarships with University of Manchester, who are the leading corrosion education institute in the UK. So we currently provide both undergraduate and postgraduate scholarships to UOM. Next one. And as I mentioned before, we have our new Chartered Engineer Direct scheme so that members joining I-Corps can progress directly through I-Corps to Chartered Engineer status. And we already have our existing Chartered Scientist scheme for those with a more research focus. Thank you. That's for myself finished, but I'll hand over now to my colleagues on CSCP. Thank you.
Right, thank you, Steve. So up next, we've got Bowie for him to give a brief introduction on CSCP.
Hi, good evening and good afternoon, everyone. I'm Bowie Zhang from Chinese Society for Corrosion Protection, and also I'm from University of Science and Technology, Beijing. I will give a brief introduction about CSCP. And now who we are. CSCP now is a member of China Association for Science and Technology. It was founded in 1979. We have now over 8,000 individual members and 287 group members. And also we have 7 working committees and 25 specialized committees. And similar to I-Corps, we have different branches which are located at Beijing, Shanghai, and 15 other provinces and cities. And this our president, Professor Xiaozhang Li, who given opening remarks in the first the lecture, and Professor Cheng Xuequn, who is also in University of Science and Technology, Beijing. And also we have 10 vice president. They are from different institutes and universities of China, working on different fields of corrosion and protection. And now what we do mainly focus on 5 different aspects. The first is to provide academic communications platforms and we will held different kind of corrosion and protection conferences, including the domestic ones and also international ones. And also we do some science popularization. We also have our maybe Chinese magazine and journal, and also we provide industry service to the including the training, education, consulting to the industry of maybe offshore engineering and oil and gas industries. And also we will issue some standards and awards in corrosion and protection. And also we have conducted strong international relations with different institutes or organizations in different places, different countries. And now CSCP is a member of International Corrosion Council and World Corrosion Organization. We are also a co-founder of Asian Pacific Material Corrosion Association. And we had established bilateral cooperation with the organizations from 18 countries around the world, including the US, UK, and France and Singapore and so on. Under the cooperation, we will give this kind of corrosion awareness honor together with EFC and WCO, and also we will provide a young scientist grant to WCO, and also I think AMPP and EFC. And as for the training and the certification program, I think we have two different kind of program. We can provide the training from NACE, like the CP1 to CP4, also the pipeline corrosion integrity management, and also we have our own training and certification program. And now we have over 60 different kind of courses, and our trainees has reached over 1,020 and 200, sorry. And for the international collaborations, during the past 3 consecutive years, I think I gave the wrong version of the slides. Maybe in 2022, we held a Chinese International Materials Corrosion conference, and which is a virtual one. And last year we held this kind of 19th Asian Pacific Corrosion Control Conference in Guangzhou, and Professor Marcus from France, and Herman from Belgium, and Nick Berbelis from Australia, and different, I think over 300 participants has joined this conference. And what I missed is that the most important one is that we had a Congress, the 22nd International Corrosion Congress in Xi'an last month in October, and I think we invited over 1,020 participants to this big event, and it was really a success. Okay, that's for the brief introduction of CSCP. You can refer to the official website or this WeChat group account for more information. Thank you.
All right, thank you, Boe. So before we begin our presentation, I'd like to note that the session is being recorded, and if you have any questions, please enter them in the Q&A box. They'll be addressed at the end of the presentation, and also for CPD, it'll be sent out after our 5th series of our 5th presentation. So an introduction to our presenters today, Dr. Di Wang. Di Wang is an associate Professor of Material Science and Engineering at Northeastern University in Shenyang, China. His research focuses on the mechanisms and mitigation of microbiologically influenced corrosion (MIC) in the oil and gas industry. His work aims to decipher the electron transfer mechanism of the classic corrosive microbe SRB and to investigate eco-friendly natural D-amino acids as green biocide enhancers combined with commercial biocides to combat bacteria and to improve microbial sampling methods in the oil and gas fields. Dr. Wang earned his doctoral degree at Ohio University in Athens in the United States in 2022, and since June 2022, he has continued his research in MIC in the oil and gas industry at Northeastern University. He has published 27 peer-reviewed research papers, including 16 as the first author. Additionally, he is a member of the AMPP Standard 21495 group, which focuses on the laboratory evaluation of the effects of biocides on biofilms. Please join me to welcome Dr. Wang.
Thanks for the introduction. Can you see my screen now?
Yeah, can see the.
Okay, the voice also clear, right? Okay, so now it's my turn to present my work. First of all, it's a great honor for me to present my research about the mechanism and the protection of microbial corrosion in oil and gas field. And firstly, I would show my appreciation for the invitation from the ICAO and also the CSCP. So now let me start my talk today. So my talk will include 5 parts: the introduction, research background, microbial corrosion mechanism, microbial corrosion protection, and also the real cases that I experienced in the last 2 years in the real world. First of all, I will have a brief introduction about who am I. I got my PhD degree in the microbial corrosion in the ICMT at Ohio University in 2022. And after that, I joined to the Northeastern University. So my research is focusing on the MIC mechanism and its prevention in the oil and field, and also some other fields like the soil MIC related with the oil and gas. Next is where I am from. I graduated from the Institute for Corrosion and Multiple Phase Technology at Ohio University. Our corrosion center is serving for most of the oil and gas industry around the world, and we are focusing on the top of the line corrosion, the titanium rod corrosion, and also the H2S corrosion. And my major is about the microbial corrosion, and so the right side is about the sponsors for us in the last 24 years, I think, and the BP and Shell. They are the excellent sponsors for the corrosion center at the Ohio University. And also from the ICMT, there are quite a lot of the alumni. They are working in the oil and the gas industry. And this slide shows some Chinese alumni graduated from ICMT, and now they are active in the oil and gas industry. Like for Yu Gui, he is working in the Shell, and Yang Yang and Ziru, they work for BP after their graduations. So now I am working for the Northeastern University, so I will have a brief introduction about my university. Last year, about 2023, the our university is 100 years old. And our university was born in the Tautering region, mid-war, and now it has 100 years. I was honored to see that the new president of the ICAO, Dr. Gao, he is also graduated from Northeastern University, so we are alumni, and he's an excellent from the Northeastern University. So with about 100 years of the endeavor, and our university is trying to nurturing talent, driving innovation, and also achieving excellence. I am working in the Department of Material Science and Technology, and our department is ranking among the top 0.1 based on the essential science indicator. And last year, the 100 years anniversary, our university published the first Nature and the Science paper, and also both papers are published from our department. So it's honorable for us. And now I will introduce my group. So now, for our MIC research team at Ohio University, our principal investigator is Professor Dick Xu, and he is a pioneer in the MIC field with more than 150 peer-reviewed papers and more than 10,000 citations. My research is around the oil and gas and microbial corrosion. So now in our research team, we have about 12 faculties and 2 postdocs, more than 30 PhD students and 65 master graduate students. So now we have about more than 100 young active in the MIC field. And so now in our lab, we own the ICM confocal and also the AFM for the corrosion morphology by the microbial corrosion, and also the HPLC GC IC for the physical parameter, and the gamma working station. And also because we are working in the microbial corrosion, so we have enough the microbial equipment for the microbials cultivation. So we believe that now we have enough equipment can satisfy the MIC and its related fields. So after the brief introduction about my research team and also our university, I will start the research background about my talk. So we all know that the corrosion, it can cause severe economic losses and also the significant hazards. Like there are different fields like the petroleum, aerospace, energy, and power. In almost all the conditions, there are corrosion problems. And also for this, the condo collapse in the Florida, this accident was also caused by the concrete corrosion, and the barium gas explosion is also caused by the corrosion. Like so now, the corrosion in China, the economic loss is about 3.3% of the total GDP, exceeding about 3 trillion CNY. So it's almost about 330 billion GBP. So corrosion can affect almost all the sectors of the economy and the equipment. The corrosion in the oil and gas induced more significant losses and threat to the energy security. So almost in all the sectors in the oil and gas industry, like the pipelines, the crude oil storage tanks, the offshore drilling, platinum, and also the MIC and the insulation. So last slide, I said that the corrosion losses can account for about 3% of the GDP, but in the oil and gas industry, this number can reach to 6%. So it's almost double of the normal losses. So corrosion affects almost every stage of the oil and gas field. So it impacts the lifeline of the petroleum energy. And among the corrosion in the oil and gas, the microbial corrosion can account for more than 20% of the total corrosion in oil and gas industry. I think the most famous of the corrosion, the microbial corrosion accident is about the Alaskan oil spill in 2006, and also the Arizona Canyon gas leak in 2015 in California is another big MIC cases. Also, in the publication, the ExxonMobil also reported the pipeline failure, and in CNPC, there are also some the pipeline formation. So based on the quite a lot of the accident or the cases caused by the microbial corrosion, but now the microbial corrosion, the mechanism is still not very clear. It's not like the metal corrosion mechanism. So now for the corrosion, it can because the corrosion mechanism is clear, so we can have some specific protection method like the cathodic protection or the coating to protect the corrosion. But for the microbial corrosion, the clear now is not so the mechanism is not very clear. So there is not a very effective protection for the microbial corrosion. And now there are some existing problem about the MIC research. So now the research focusing on the microbial corrosion behavior of specific materials in a specific environment. The second thing is that the microbial corrosion is related to the materials, biology, chemistry, and also some other areas. So it's difficult to have a clear mechanism for the microbial corrosion. So the key for the microbial corrosion is that to classify the MIC mechanism, it can help to navigate the design of the materials or the treatment or the suitable treatment methods to treat the MIC problem. So now in the MIC, there are some questions. I think the first question is about is there direct interaction between the microbials or the metals? The classical theory think that there was not direct interaction between the microbials and the materials. So the microbials can create a local acid area, and then the acid is the main cause for the metal corrosion. The second theory is that for some the passive metals, it can resistant the acid corrosion, but we know that some passive metals, it cannot withstand the MIC. So the classical theory cannot explain the MIC while. The second question is that why and how the microbials can corrode the metals. So now it's not clear. So based on these two questions, we need to classify the mechanism of the microbial corrosion. And based on our previous research, we have some opinion about the microbial corrosion. The first opinion is that the electroactive microbials are the main causes of microbial corrosion by extracellular electron transfer. The traditional theory see that the microbials indirectly affect the concentration of hydrogen or oxygen at metal and solution interface. But for the EET theory, the theory is that the microbials can acquire the electron from metals through the extracellular electron transfer, and it can directly involved and regulated in the corrosion process. The second opinion is the microbials can obtain energy from metals. So in the industry, there are some severe microbial corrosion pitting caused by but in the lab, it's hard to simulate the severe corrosion. So there is one thing is that in our lab research, we have enough carbon salts as the nutrient for the cells growth. So it means that if the cells, it can have enough nutrient, they won't corrode metals. But in the real world, in the industry, there are few nutrients. So it means that the microbials, they will switch to obtain the energy from metals. So it causes the severe corrosion, the severe microbial corrosion in the industry. So this theory thinks that the novel starved sulfate reducing bacteria can cause more severe corrosion. And also this opinion say that the microbials can participate in corrosion positively. The next one is about the biofilm is about the microbial corrosion protection. So the biofilm is the main reason for the MIC. It means that the mitigation of the MIC is to treat the biofilm. So the strategy is to transform from the sarcoph cells in the biofilm to the planktonic cells. This strategy is that to make the hard-killed cells to the easy to be addressed cells. And also for the biocide use, it can induce other problems like the environmental problem. Because of more and more strict regulation, the large doses use of commercial biocides is not a suitable way. And also because of the resistance of the microbials, one continuous use the commercial biocides, even though you use in a higher corrosion, but it cannot have a good efficacy. So the problem need to be solved is that we need to find the low cost and no drug resistance to address the microbial corrosion. And based on this goal, the amino acid in it was found to prevent the bacterial adhesion, and also it can disrupt the electron transport chain. It can achieve protection against the microbial corrosion. But for the amino acid, we need to use biocide and the amino acid together to have good efficacy. So with the combination of the commercial biocide and the amino acid, the combination can transform the corrosive, hard to kill sarcoph cells to the non-corrosive, easy to kill the planktonic cells. And also it can disperse the biofilm. And also some biosynthesized the amino acid chain can also enhance biocide on the mitigation of corrosive biofilm. So the use of the amino acid can reduce the biocide usage and address the biocide overdose. And finally, it can achieve the eco-friendly goal. Next part is the microbial corrosion mechanism that I did before. So the first work I want to introduce is about the SRB mechanism. So in 1934, there is a theory, we call it CDT, the cathodic depolarization theory. So in this theory, the founder said the SRB can secrete hydrogenase. So the hydrogenase can lower the activation energy for the dispersion of hydrogen atoms and consume molecular hydrogen. It can cause a depolarization effect. So this can promote the cathodic reaction and then accelerate the corrosion. So the key for this theory is that the hydrogenase is a key role in the SRB corrosion. So based on this theory, we designed the experiment using the starvation experiment. So under the carbon salt starvation, we found that a model SRB strain, it can, under the starved condition, it can has less thickness of the biofilm, but it can induce more severe localized corrosion under the starved condition. So whether it's related with the hydrogenase or not, so we use the molecular method to see the hydrogenase genes change. And after that, we found the hydrogenase genes of HYDA and HYDB, they are upregulated. So the upregulation of the hydrogenase genes can help to explain that the hydrogenase might play an important role in the SRB corrosion. But it was not totally confirmed about the hydrogenase. we can only see that it's possible. And so based on this work, we use the molecular tool to create a hydrogenase deficient strain of the SRB, and also we use the two strains. One is the wild type of the SRB, the other is the hydrogenase deficient strains. So we use these two strains to compare the microbial corrosion. And after our experiment, we found that the wild type SRB strain can corrode more corrosion than the hydrogenase mutant strain, but the hydrogenase mutant strain can also induce corrosion. So it means that even though there is no hydrogenase genes inside, there is still microbial corrosion caused by this strain. And after this result, we designed another result. We use, because the sulfate reducing, it reduced the sulfite to sulfate to the sulfite. But for one SRB, it can also use fluorite as the electron acceptor. So we use one strain, and for this strain, it can use fluorite and sulfate as electron acceptor. And we also compare the corrosion. We found that when the sulfate was used as the electron acceptor, the corrosion caused was more severe. So it means that the biogenic produced iron sulfite is also play an important role in the corrosion of SRB. So this work used the hydrogenase deficient strain to confirm that one thing is the hydrogenase mutant. The hydrogenase it can contribute part of the SRB corrosion. The biogenic produced iron sulfite can also play part roles in the corrosion of SRB. So the SRB corrosion is not influenced by one impactor. It was influenced by several inside impactors. And after that, because last work is about to compare the inside of the SRB itself. So is there other impactors that can influence the SRB corrosion? So we compare the medium, because for some of the SRB, the medium has the freshwater medium, and also the seawater medium is also used to cultivate the SRB. So the main difference in the medium is that the chloride concentration. So based on this hypothesis, we think that the chloride concentration is also an important impactor on the SRB corrosion. So we have this work to design the different chloride concentration. So in abiotic condition, we all know that the chloride can induce abiotic corrosion, but in the biotic, there is one problem, is that because if the chloride concentration it's different in the medium, it means that the strain cannot live in different conditions. So we can compare we can compare the human and the bacteria. So if human in a high temperature and a lower temperature, it's also hard for us to adapt to the environment. And also for the bacteria is the same. So finally, we adapt the model strain of the vulgaris from the fresh water to the seawater to increase the chloride concentration step by step. And finally, this strain can adapt to the conditions of different chlorides. And finally, we found that influence of the chloride on the strain on this SRB strain is also an important impactors. And these are some electronic results and also the corrosion products. And then we use two different media with the same chloride for one strain. And also we found that even though the chloride concentration, they are the same, but the corrosion rate caused by the same SRB, they are totally different. So for the SRB strain, the corrosion rate is media dependent. So in last two works, I introduced that the microbial corrosion of SRB. The first is that it was influenced by itself, the hydrogenase, and also the biogenic sulfides. And also the other thing is that the media composition is also an impactor for the microbial corrosion of SRB. The next part is the microbial corrosion protection I will introduce. The first is the shale microbiome MIC mitigated by the biocide combined with the amino acid. And this shale microbiome was combined was collected from the Weiyuan campus, from the Weiyuan Platinum in the Sichuan province. And based on our analysis, we found that the sulfate-reducing bacteria are dominated in our tested shale gas microbiome. And then we have different composition of biocide and the amino acid. And with the addition of the amino acids, the biofilm coverage reduced, and the biofilm can also disperse from the carbon steel surfaces. This is the corrosion and electrochemical data. And also in our research, we found that when we use the D-tyrosine, when this amino acid at a very low dosage of 1 ppm, it can enhance 50 ppm dBMPa. The next work is a biosynthesized peptide. This is a loop amino acid. It can also work as biocide enhancer to mitigate oil MIC in a flow loop. And for this peptide, it can, when it was in about 180 ppb, it can enhance the dBMPa, mitigate the MIC caused by the consortium from the oil field. And also, except the amino acid, we also cooperate with other researchers to synthesize some eco-friendly biocides. And for this one, we synthesized the RTRQAS biocide. And when this new biocide at 50 ppm, it can kill most of the divagarous cells on the X80 carbon steel surface. And also we use the electrochemical tool to compare the RTIQAS with glutaraldehyde and also the THPS. We found that at the same concentration, the RTIQAS or synthesized biocide is better than the THPS and the glutaraldehyde. And also for this part, and also based on, because last part is about in anaerobic condition to mitigate the SRB corrosion. And also we confirm this biocide can also reduce the stainless steel microbial corrosion by aerobic Bacillus ricciformis biofilm. So it means, so we confirm that this biocide can be worked in both conditions, anaerobically and aerobically. The next part about the microbial corrosion is we have the antimicrobial performance of RCB steel with copper chromium addition produced by China. So in this part, we compare the RCB steel with the addition of copper and the chromium to compare with X70 carbon steel. So we have some corrosion product analysis. And based on the electrochemical results and also the localized corrosion, we conclude that with the addition of copper and chromium, the alcohol, the pitting, and also the white loss decreased, but the MIC still occurred. So it means that when we have some novel steels that we want to use in the market, we need to compare the cost and also its achievement. So we need to compare the cost and also its achievement. And the fifth part is that the real cases are experienced in last 2 years in the real world. And the first thing I want to say that we always see the microbial corrosion, it was caused by the sulfate-reducing bacteria. The SRB is the most important, and also it was most investigated in microbial corrosion. But in my experience, I found that in different platinums, the microbial composition, they may be totally different. Like for this one, I collect the microbials also from the Sichuan province, but in this analysis, we found that there was no SRB inside. This strain can attribute to more than 90% of the microbial compositions. So in different platinums, in different platforms, there may be different microbiomes. So when we used biocide treatment to mitigate the microbial corrosion in one platforms, we need to know the microbiome composition in this part, and then to have a suitable biocide treatment for it. The second thing is that the microbiome collected under the insulation. So in this part, I found that the microbial composition in different direction of the pipeline, like in the top and in the 3 o'clock, they are totally different. So after the analysis of the microbiome of the pipeline under the insulation, I found that the microbial samples at 12 o'clock, it has more kind of microbials than the 3 o'clock. And also it introduced more localized corrosion. So it can help to explain that the microbial corrosion under the insulation is more severe on the top of the pipeline. And it can give some hint for the real world when we use the coating or use some other method for the pipelines. We need to focusing on the top side of the pipeline. The third part is that the microbiome collected from the different stages of the oil field, like for the injection and extraction. We need to see that in which stage it can contribute to most of the corrosive microbials, and then to focusing on this stage or several stages to treat the microbial corrosion. For some unimportant stages, we don't need to use more power or biocide to treat the problem, because it's in some stages they are not relevant to the microbial corrosion problem. The fourth part is that so now the modified postgate B media, the MPB, is mostly used in the cell counting, and the MPB media was formulated by the SRB research John Postgate, and also this media is also in the NACE standard for the cultivation of SRB, but the standard may not totally right, especially in the real world. Like based on my research, the chloride concentration in the shale gas, and the higher chloride and the lower chloride, it can have different the cultivation for the SRB. So the next part is some mild devices for the MIC in the real field. The first is that we for the microbial samples, we need to have adequate and timely microbial sampling when facing the MIC failure. And then based on the microbial sampling, we need to have the lab simulation using the molecular biology tools and to find the main microbials in the MIC based on the literature or the machine learning. And when we know what's the important microbials in the sample, we can have the corrosion test and the biosite evaluation in lab based on the classic samples. And also for some samples, they are in the flow rate. So for the MIC mechanisms, the flow loop system is also important to mitigate the MIC. And also we need to have some, we need also to focusing on the flow loop MIC problem. So about is all my presentation. Thanks for your attention. And below is my personal information, my email, my mobile phone number. And also I registered LinkedIn, but now I don't have access to log in, but you can find me on LinkedIn. Okay, so that's all my presentation.
Right, thank you. Thank you, Dr. Wang. So we are going to our Q&A session right now. So for our first question, it's from Steve Tate. It's a comment and the questions. It was good to see the GDP broken down by industry for cost corrosion. 6% is a very significant cost. So is there any evidence that this cost is trending down with the new technologies?
Oh, it's a good question. So for the 6%, it is statistic data that I found in a Chinese website published in 2022, I think. So the 6% is the most recent data.
Right. And also, there's no standard solution, and each producing field requires its own analysis for development and treatment
There
regime.
is no standards.
Very good. Yeah, I think it's just a comment. And for our Q&A box, first question is from Muhammad Arsalan Shams. How to control MIC corrosion if the bacteria is present in the soil and attacking the pipeline's external surface?
No, for the microbial about the soil, so it's a good question because like in the soil environment, we cannot use the biocide like the internal microbial corrosion. So my opinion is that the coating and also the coating now is still the most efficient way for it. But based on my experience about this, like in the top side and the other side, the corrosion caused by the microbials, they are different. We need to try to focus in some important direction and also to put more efforts inside to help to reduce the corrosion. But so this is the first thing. The second thing, I think that the coating is still the most efficient way. For other way, like the biocide is not, I don't think it's useful in the external, especially in the soil environment.
Right, yep, thanks for that. So the second question is from an anonymous attendee. Can MIC occur on CRA?
In fact, for this question, I cannot say yes or no because I don't know. I don't have the experience here about microbial in CRA.
Right, okay. And the next anonymous question from an anonymous attendee. Hello, Dr. Wang. What are your thoughts on the effect and influence on sulfate-reducing alkia? Do these also respond to mitigation using biocide enhancers?
Oh yeah, for this one, it's a good question. Because for the sulfate reducing bacteria, that's the most investigated because the temperature is about 30 to 40. But in my opinion, in my experience, the sulfate reducing archaea is almost grow at the temperature about 70 to 80, I think. For this part, the biocide enhancer is still harmful, but because for some of the biocide enhancer, they want to lose the activity at 80 degrees C. But for some biocides, we need to see whether it can have the activity or not. Like in my opinion, the glutaraldehyde cannot effective in at the temperature of 80, but the THPS, it can work.
Right, thank you for that. And the next question is from Zubair Ibrahim Saib. Any reasons for not choosing the 6 o'clock position for the MIC study for corrosion under insulation?
Oh yeah, for this question is that's about the real problem in the real world, because when we collected the samples, when the industry they are trying to repair the pipelines, and we have some the real picture, and we found that at the 12 o'clock the localized corrosion that's the most severe, but in the 3 o'clock, 9 o'clock, and 6 o'clock, we found that the real corrosion, they are almost the same. So we just use the 3 o'clock sample to as a representative and to compare and use this representative to compare with the most severe at the 12 o'clock.
Right, and next question. Given the lab research into parameters that affect mechanisms, can we apply this understanding to industrial setting? For example, can we, if MIC is likely in the particular system? Can we apply this understanding?
I don't quite understand this question.
Yeah, I think
What's
it's
the mean?
related to one of the previous questions. So whoever that asked this, can you please clarify? And I'll go to the next question. So the next question from an anonymous attendee: how is the microbial corrosion affecting offshore pipelines?
Oh, for the offshore pipeline, I think there are still the microbial corrosion, and also for the offshore pipelines, there are also the highway pressure, and I think that the highway pressure is also a main factor for the microbial corrosion, because I think that at the offshore environment, the strains, they are totally different, like we do in the lab simulation, because the pressure is a key impactor, I think.
Right. Okay. And the next question from Lloyd Potts. Thanks, Dr. Wang. Great presentation. Did you test the threshold of what chloride concentration result in a decrease of cell activity? For example, testing higher than 400 mm.
Okay, so so I think that your question is a little different from the goal that I did in that project, because in that project I want to try to make the strain to alive in different chloride concentrations. So when I found that it cannot alive at the the relatively higher concentration. However, to make it to adapt more and more time to make it can adapt in the higher concentration. So my goal is to make it to make the strain can alive in different stages. But so I want to try to make the strain to exceed the threshold.
All right, thanks for that. So I'll take one more questions because we're at 1 o'clock today. So it's from Sunday Sampson. What is the best way to control MIC from the soil side of storage tank using vapor space corrosion inhibitor when there's no cathodic protection?
I think for this question, I don't have a good answer because for the soil microbial corrosion, I want to say that I only have some experience from the April of this year. So for the strategy to how to control the soil microbial corrosion, I don't have the experience now. But I think that the coating is still an efficient way to deal with it.
Right, okay. We could probably take one more question. It's from Vijendra Kumar Singh. Can you suggest which material is best and worst on the basis of their performance against MIC? So material, carbon steel, aluminium, brass, copper nickel, or copper nickel 70-30% or 90-10%, or duplex stainless steel?
I think it's, for this question, I think it's we all know that the duplex stainless steel is the best among them, but in the real world, we also need to consider the cost. So, like for the for the pipelines, even though we know that some materials they are much better than the carbon steel, but the pipelines is several hundred kilometers long. So the cost is the most important to choose the materials. So for the pipeline, the carbon steel is still the first choice. So when we chose the materials, we need to consider the performance and also the cost. So we need to negotiate this to find the best way. Now, I think that the best materials it can help to against the MIC, but the price is quite higher, so it cannot help to solve the problem very well.
Yeah, right. Thank you for that. And with that, we are going to end our webinar for today. And if you've got further questions, you've got Dr. Wang's contact details on the screen. And please feel free to reach out to him. And with that, I'm going to end the webinar today. And I'll see you guys tomorrow. Thank you all.
Thank you. Bye.
Okay, thank you. Bye bye. Have a good day.
Thank
Have a
you.
good
Bye.
night.
Thank you,
You too.
Dr. Wang.
Okay, thank you for